Hey everyone. Hopefully everyone's staying warm and healthy. You have power and internet and water and all of the main essentials of life. Um, so, the video today, I'm trying to figure out what we can do, what we can talk about that's not too far off of kinetics, because we still are going to be taking our free response portion whenever we get back. So I don't want to go too terribly far out. So what I'm going to be doing is talking about potential energy diagrams. This is going to go into a little bit more of thermo. It's kind of the thermodynamic side of kinetics. There's going to be a few things in this little worksheet that I'm gonna run through to that we haven't talked about before. So as they come up, I can talk about them a little bit. Okay. Let's do this. So as a quick reminder, in case this is the first time you're hearing this, all of AP Central assignments are open. All of the progress checks are open. This year has been absolutely awful. If you are missing something, turn it in. They remember my late policy is it's a 0 until you turn it in, at which point I grade it. I'll grade it eventually, and then you got it. So don't think that, oh, I haven't turned it in. I guess I'll never turn it in. No, still work on it. Turn it in. Jeez. Everything we do builds on each other. So if you're not getting a topic, it's going to be hard for you to go on to the next topic. So if you're missing work, go back, work on it. We'll do it. I know it's a bit of work, but that's what it is. All right, let's actually do this. So as a quick reminder, when we're talking about potential energy diagrams, here we go. We have a potential energy diagram right here. First step, label the axes. What is the axes here? So we know this is our reactant on our product. So this is our reaction moving forward in time. There. This is our energy. In particular, this is kind of our chemical potential energy. So when we're talking about kinetic energy, that's the temperature, right? That's the how much temperature is there. That's the them moving around, vibrating, rotating, and all of that. This is chemical potential energy. This is how much energy is stored up inside these the products and the reactants. All right. So what does each curve represent? So here, this looks like it's one reaction. This looks like it's the same reaction, but with this curve goes up higher. So there's two different reactions going on here. So I'll just put two reactions. What type of reaction is occurring in terms of energy flow to and from the surroundings? So, in terms of energy flow to and from the surroundings, remember what you want to look at is where your reactants are, where your products are, and it looks like we're going up here. So that means this reaction is gaining potential energy. Energy is going into this reaction from somewhere. So from the surroundings, that if the reaction itself is gaining energy, where does that energy come from? It comes from the surroundings. So energy is leaving the surroundings and going into the reaction. This also means that this is an endothermic reaction because energy is going into the reaction. All right. So they have that. Now, what does each number 1, 2, 3 represent? So here, this looks like an activation energy. An activation energy is the beginning reactants and then all the way to the very tip top of the hill. This is that activation energy. The things that are going on up here, let's say this is A, we'll say AX plus B, and over here we have A plus BX. Up here in this section, what we have is AXB. All of them together, all of them bound together in some weird way. So, this is going to be a very unstable molecule. This is going to have a lot of potential energy. So, it's going to be way up here. All right, so this is that activation energy, or E sub A. E sub A is when I say sub, I mean the little subscript down here is an A. Energy, subscript A, E sub A, is the activation energy. It's a kind of energy. Activates. All right, so there's that. We know that this is going to be the blue's activation energy. Number 2 is going to be the red's activation energy. It's the same thing, but just that. We know that the red is underneath the blue. So we can say that we can kind of surmise and infer synonyms that the red here is going to be a catalyzed reaction. It's the same reaction, just at a smaller activation energy, which means that an enzyme is doing something to lower the activation energy down. This big one is probably an uncatalyzed reaction. Yeah. The quick aside, catalysts can actually increase activation energy. A catalyst is just something which gives an alternate reaction mechanism, different steps, different elementary steps that we can go through. So a catalyst can definitely make the reaction go slower if need be. So it just changes that activation energy. Typically that never happens. We never really want it to happen. We want things to go faster. So that's why I just said automatically red is catalyzed, blue is uncatalyzed. But technically it could go either way. But that's an aside. Yay, you get my asides again. All right. Next one. Here we have a multi-step reaction. Speaking of, so anytime we have a reaction that has multiple steps, those elementary steps, then we're going to have an activation energy similar to this. We still have our reactants, we still have our products, but now we're going to have multiple peaks going on. So if it's a multi-step reaction, we're going to have multiple peaks, multiple things. All right. So what is the overall activation energy for this reaction? So the overall reaction energy for this reaction, you start at the reactants and you go to the very tip top thing. Okay? And we know the reactants are at 0, as it says. The X up here is at 60. So we know that we have 60, and look here, kilojoules. 60 kilojoules is the overall activation energy. I said overall. Now, if I said, what is the activation energy for the second step? That's a different question. The second step is this second peak here. This is going to be where we start the second step. We don't start the second step down here. All right. All right, so B, what is the reaction enthalpy, delta H, of this reaction? So this is something that's new we're talking about. When we say delta H, that means the reaction enthalpy. That means what is going on with the energy of this reaction, the potential energy in this reaction. Is it leaving? Is it gaining? What's happening? So we start here at our reactants, and the enthalpy of the reaction, we are losing energy. We're going down to our products. And in fact, it even has it right here, negative 35. So the reaction enthalpy, the delta H, is negative 35 kilojoules. Okay? That's what the delta H of this reaction is. So if you hear me say delta H, again, that means the enthalpy, that means energy, what's going on. So if I said that the delta H of a reaction was positive 60, that kind of tells you something. This positive tells you that it is going to be, the reaction is going to be gaining energy, which means it's going to be pulling energy from surroundings, which means the reaction is going to be endothermic. It's going to get colder. Things around it are going to be getting colder. All right. If it's negative, like here, negative 35, that means the surroundings are going to gain energy. The surroundings are going to be hotter because energy is exiting the reaction. All right. Is this okay? What is the rate determining step? What is the thing that has the biggest activation energy? Which step has the biggest activation energy? So let's look at the different steps here. We're moving this way in our reaction. So here, the first step has this reaction energy. So we even can label these numbers now. This is 50. This one is, what, 35? 35 to 60. So that's what, 25, and then this is 5. Okay, so we can tell right off the bat the first step is going to be our biggest activation energy. Okay. All right. Is the reaction exothermic or endothermic? We've already talked about that. This is going to be losing energy. The reaction is losing energy. It's exiting the reaction. So this is going to be exothermic. Which letters represent activated complexes? Activated complexes is another term for transition states. Trans states. All right. It's the same thing. Activation complexes, transition states, two terms that mean the same thing. So there's that. So that means which ones are the activated complexes? V, X, Z. Those are going to be your high energy things that aren't going to stick around very often. And then which letters represent reaction intermediates? Intermediates are things that stick around for a while. These are the little valleys. You can imagine if there's this is a car running up here. You can understand like, this might lose energy right about here and fall back into this little valley. That means we have an intermediate right here. So intermediates here, transition states or activated complexes right there. Okay. All right. Next one. We have 3 different potential energy diagrams here. All right, so which ones are described by each of these statements? An exothermic reaction that is unlikely to occur at room temperature. So out of these 3, which ones are going to be, which one is going to be unlikely to occur at a room temperature and is exothermic? So exothermic, right off the bat, you know that number 1 cannot be it. Number 1 is gaining energy. So can't be number 1. Number 2 and number 3, though, are both losing energy. So that means that it's exothermic. Which one is unlikely to occur at room temp? Now remember, if we are, I'm going to use this site over here. Remember those little distributions, temperature distributions we talked about. where let's say if it's at room temp, let's say this is, we have kinetic energy and we have number of particles. So if something is at 40 degrees, you might have something that looks like this. The average is right here, but some are actually quite a bit higher than that, right? But if we have, let's say, the same number of particles, but if we have 60 degrees now, the average is right here, and now we have a bunch more things going across. So think about this whenever you're answering this. What is unlikely to occur at room temperature? Not possible. This is not impossible to occur at room temperature, but just unlikely. The answer is the one with the larger activation energy. Okay? So we have to have a certain amount of kinetic energy to jump over this hill. That, if we go back to this, these guys, there's still going to be a few over here that might actually make it up over this hill, but it's not going to be very likely. If we're higher than room temperature, we're going to have more particles that have enough kinetic energy to jump over this hill. Okay, there's that. So the answer number A is 3. An endothermic reaction. Well, we already talked about that. This one's the endothermic. The other two are exo, so this is 1. The E sub A is greater than the energy released. So, just looking at this, here's the activation energy for number 3, right? It's pretty big. And this is the energy released. This is our delta H. So this case meets C here. Here, this is our activation energy. Whoop. This tiny little amount here is our activation energy, right? And we have a very large delta H. A lot of energy leaving the reaction, exiting the reaction. Number 2, this is kind of like a match, right? All you got to do is just little spark, and then all of a sudden it puts out a bunch of energy. Okay. This, I'm trying to think of a good example of this. A bunch of work for a little bang. Yeah. I don't know. I can't think of a good example. A joke. This is like studying a week straight for an exam and making an 89. A whole bunch of work, but a little bit. I'm joking. All right. A spontaneous exothermic reaction. Spontaneous just means it just happens. It's going to happen pretty easily, and that's going to be number 2. Okay. Spontaneous is the word we use if things just automatically happen. We don't have to put a lot of energy into it. Okay. All right. Draw a potential energy diagram for the reaction that has negative 80 kilojoules per mole and a 28 kilojoule per mole activation energy. Label axes, activation energy, delta H, site of the activated complex. Again, we're going to just cross this out and put TS, transition states, reactants and products. All right, I think I can do this right here. This is going to be my potential energy. This is going to be the reaction progress. And it's a negative delta H, so that's about right. And so from here to here is negative 80 kilojoules. And from here to here is positive 28 kilojoules. If you wanted to get fancy, you can just say that the potential energy up here is 0. And then you can just put your axes there, 28 and negative 80. There we go. A lot. That's actually what we do a lot of the time. Is that because we only really care about the change in energy, we don't actually need to define what our reactants are. We can just say our reactants are 0 and use that as kind of a starting point, because we usually only care about the change in energy. Okay. All right. And this is our reactants, and this is our products, and this is our transition state. So there we go. Using potential energy diagrams for an endothermic and exothermic reaction shown, choose the letter that best fits each statement. All right. The potential energy of the reactants. So, the potential energy of the reactants. Sure, I guess it would be C, is how I would call that, and then R for this one. For the products, say E and Z. The reason I'm saying this is, I just told you that it's kind of, we care more about the change than we do about these actual energies. Yeah. All right, delta H of the reaction. So the delta H, again, the change in the energy from reactants to products. In this case, reaction 1, it's going to be B. Reaction 2, S. So the delta H of the reaction is, when you go from reactants to products, just like that. The activation energy of the forward reaction. This is specific here. Forward reaction. So we are moving this way, which means we go from here all the way up to the top. D. Here, we're going forward. Starts here, goes up to there. T. Site of the activation complex. A. So again, it's right up here. So A and W. The energy of the activation complex, the activated complex, is A or G. G and X. The activation energy of the reverse reaction. So in this case, we're moving the opposite direction. So we're moving this way. So we start here and then move up to here. F, Y. All right. Okay. So that's all I'm going to really talk about right now. I'm going to leave this for you guys. If you've watched this far, do this problem. I'm going to leave it up on the screen. Yeah. So go through, do this, and see if you can do number 4. If you can do it, take a picture of it, and then send it to me. Awesome. It's going to be just a quick one problem to do. It's not going to be worth very much, like 5 points. Something very, very minimal. All right. Have a good one, guys. See you guys Thursday? Maybe?